Hey everyone, today we are opening up the mathematical toolkit to really master the art of counting. And no, I don't mean just 1, 2, 3. I mean figuring out the odds of a card hand, or how many ways a team can line up for a photo, all without listing every single possibility. We're going to break down 3 really powerful techniques for problems that use the words or and not, and you'll see how sometimes the easiest way to count what you want is to first count what you don't want. All right, let's dive right into our first tool. We'll start with a scenario that's all about making one choice from a few different groups of options, something anyone thinking about life after high school knows very well. So here's our first little puzzle. Sydney's applying to universities, and she's got options spread across 3 different schools. Now, before I just give you the answer, take a second. How would you figure out her total number of choices? It's pretty straightforward, right? I bet you already have the number in your head. And there it is, 7. You just add them up. 2 choices at Waterloo, plus 3 at Queen's, plus 2 at Laurentian, that gives you 7 total choices. The key thing here is that picking a program at Waterloo means you can't also pick one at Queen's, right? They're totally separate options. See? You already get the basics of our very first tool. Okay, so let's put a proper name to what you just did. This is called the rule of sum. It's super useful, but it comes with one really important condition. The whole thing hinges on that phrase, mutually exclusive. It sounds fancy, but all it means is that the events can't happen at the same time. Sydney can choose a program at Waterloo or at Queen's, but she can't be enrolled in both at once. As long as the choices are separate like this, you just add them up. It's that simple. Now, this is a spot that trips a lot of people up, so it's really important. The rule of sum, our OR rule, is for when you're making one choice from separate pools. That's when you add. The fundamental counting principle, on the other hand, that's for when you're doing things in a sequence, like picking a shirt and pants. That's when you multiply. Getting that or versus and difference is the whole secret. So the rule of sum is perfect when our choices are all neat and tidy. But what happens when life gets a little messy? What do you do when your options start to overlap? Okay, let's take on a trickier problem. We're dealing 3 cards. We want to know how many ways they could all be face cards or all be red cards. That word or is a huge clue. But hang on, can we just add the 2 possibilities together like we did before? Let's investigate. First up, let's count the ways to get 3 face cards. So there are 12 face cards in a deck. And because the order we deal them matters, getting a king, then queen, then jack, is different from getting a jack, then queen, then king, we have to use something called a permutation. The calculation for that, 12p3, gives us 1,320 possible ways to get 3 face cards. Okay, so far, so good. All right, next, the red cards. There are 26 of those in a deck. And again, since order matters, we calculate the permutation of choosing 3 from 26. That gives us a pretty big number, 15,600 ways. Now, if we just added those 2 numbers together, we'd get a massive total. But it would be totally wrong. Why? Aha! Here's the catch. We've counted some cards twice. Think about it. The Jack, Queen, and King of Hearts, and the Jack, Queen, and King of Diamonds. Those 6 cards are both red and they're face cards. So they got counted in our face card group, and they got counted again in our red card group. We've got to find a way to fix that double count. And this brilliant little formula is exactly how we fix it. It's called the principle of inclusion and exclusion. It basically says, yeah, go ahead and add the possibilities for event A and event B, just like we wanted to. But then, and this is the genius part, we exclude or subtract the possibilities that got counted twice because they belong to both A and B. It's the perfect tool to clean up that overlap. So let's put this thing into action. We take our 1,320 ways for face cards, we add the 15,600 ways for red cards. Then we subtract that overlap, the number of ways to arrange 3 of those 6 red face cards. That calculation, 6 permute 3, is 120. Do the final math, and there's our correct total, 16,800 ways. All right, we have handled OR problems, both the simple kind and the overlapping kind. But now let's switch gears and look at a totally different challenge. Problems that have the word not. Believe it or not, sometimes counting what you want directly is the absolute hardest way to do it. Check this out. A basketball team of 12 players is lining up for a team photo. How many different ways can they line up if the captain and assistant captain are not allowed to stand next to each other? Now, if you tried to calculate this directly, oh man, you'd have to figure out every single possible arrangement where they're separated. It would be a complete nightmare. There has to be a smarter way. And there is. It's called the indirect method, and the logic behind it is just beautiful. Instead of counting all those complicated ways they can be apart, let's just figure out the total number of ways they could line up with no rules at all, and then subtract the one simple case we don't want, which is the case where they are together. Think of it like this. Why would you count every single girl in a class one by one? If you already know the total class size and you know how many boys there are, it's way faster to just take the total, subtract the group you don't care about, and what's left over is the group you do care about. Okay, so let's apply this. Step 1. What's the total number of ways 12 players can line up with 0 restrictions? Well, that's 12 factorial, which is just a fancy way of saying 12 times 11 times 10, all the way down to 1. And it is this ridiculously huge number, almost 480 million ways. All right, now for the clever part. We are going to calculate the one scenario that we want to get rid of, all the arrangements where the captain and assistant captain are standing side by side. So to do this, we use a little trick. We treat the two of them as a single unit, almost like they're glued together. So now, instead of arranging 12 different players, we're really just arranging 11 items, the 10 other players plus our new 2-person block. That's 11 factorial. But wait, within that block, the 2 players can swap spots, right? So we have to multiply by 2 factorial. That gives us just under 80 million arrangements where they are together. And now for the final satisfying step. We take our total number of arrangements, that massive 479 million, and we simply subtract the number of arrangements where they are together. And what's left is our answer. Over 399 million ways for them to line up where they are not standing together. So much easier than trying to count that directly. And there you have it. You've just added 3 incredibly powerful techniques to your problem-solving toolkit. Let's just do a quick recap so you know exactly when to use each one. So when you see an OR problem and the options are totally separate, use the simple rule of sum. Just add them up. If that OR problem has choices that overlap, you got to upgrade to the principle of inclusion-exclusion, add them both, then subtract the messy part in the middle. And when you see a problem with that keyword not, think smart, not hard. Use the indirect method, find the total, and subtract what you don't want. Just think about the password on your phone or computer. The rules probably say something like it needs to be 6, 7, or 8 characters long, using letters or digits. Every single one of those ORs points right back to the tools we just talked about. So the next time you type in that password, take a second to appreciate the absolutely astronomical number of possibilities you're actually protected by. It's pretty amazing.